Greetings, welcome back to Randomtronic. My name is Chris. Today I want to talk about RMS and RMS measurements, RMS multimeters, and is RMS really root mean square or really mean sales tactics? Some time ago I did a video with the Aneng really inexpensive True RMS multimeter, and I've put a badge on it calling it False RMS multimeter. That caused an avalanche of responses in the video saying that did it wrong, there was a issue with my measurement, or the frequency was out of capability of the multimeter, out of the bandwidth that it was designed for. Those things were somewhat true. However, not exactly I was wrong, and I want to show you today why. You see, RMS or root mean square is a way of measuring an AC signal, AC voltage or current or power, you name it, in such a way that you will get an equivalent value of a DC voltage or current that would cause the same heating effect in a resistive element. That's why the RMS is also sometimes referred to as the heating value. Now, if you think about it, heating effect does not matter on the polarity. It doesn't matter which way the current is flowing, it is still causing a heating effect in an element. That's why, and I will show you that in a moment, when you look at symmetric square wave, the one that goes plus and minus the same value, the RMS of that signal would be the peak value of the positive peak value of the signal. So if your square wave goes to plus and minus 2 volts, the RMS value is 2 volts. Now it gets a little bit more complex with other waveforms, like for example sine wave. Because the sine wave is constantly changing, it is not that simple to calculate it or just take a value, because a lot of it depends on the shape of the waveform and so on. Now, if you're dealing with only one type of waveform, so for example, let's take a sine wave. If you're dealing with a sine wave, it is possible to calculate the RMS value of that sine wave, and it will be reasonably accurate. And that's what averaging multimeters do. They have a lookup table or of some sort inside the microcontroller. They measure peak value and they look up the value of the RMS signal for that, and that's what they display on the screen. However, a true RMS meter works entirely different. It's supposed to measure the entire signal, not depending on the waveform that it's dealing with, and display the heating value or the RMS root mean square value onto the screens. So when you're doing a measurement, you know exactly what sort of power levels you're dealing with. That's the idea of the RMS measurement. I've got two highly advanced charts prepared on here. So let's start maybe with a sine wave. There are complex ways of calculating the actual RMS value, but an easy and quick approximation is to divide this into multiple points, take individual measurements along the waveform, then do the root mean square. With a sine wave, to get an accurate reading, you would need to take quite a lot of points, quite a lot of measurements here. So at first you do one here. The important thing is that the measurements are at equal intervals. Take a reading at this point, this point, this point, this point, and so on. You get the idea. By taking all those values, this would probably be not enough to get an accurate reading, but you know, if you keep adding measurements in between the other ones, you probably get close enough to get enough points to get an accurate reading. The formula for that would be, it's a root, that's in the root mean square, V1, V2, it would be V1 plus V2 plus V3 and so on up to, we call that Vn, divided by the number of the measurements that we took, so divided by n. So that's the mean value, and then there is the square. So each of the voltages have to be squared individually before being added up. That is the formula for approximating the RMS value. The important thing to note that there is no frequency element in this equation, and the RMS value is entirely independent of the frequency of the signal. As long as the shape of the waveform and the amplitude doesn't change, the frequency can change as much as it wants, and it doesn't matter. The RMS value of that signal will still be the same. However, it is important to remember that the circuitry inside a multimeter is limited in frequency, has its own bandwidth. So once it goes past that bandwidth, the multimeter is unable to make all the measurements that it needs. Things happen simply too quickly, and the multimeter is not keeping up. That's when you start getting false readings. Let's have a look at a square wave. And this is an example of a symmetrical square wave. That's what I said. If this is 0 volts, it will go to -1 or minus whatever arbitrary value you want to put in here, call it X or voltage peak minus voltage peak and so on. So it goes in the same way both directions. RMS value of this, to get it using this approximation form, it's actually quite easy. All we have to do is take a measurement at each of those points, because the waveform is not changing anywhere in between. If we take a measurement here, it kind of covers this area and it covers this area, and then the duty cycle also doesn't matter in a case of a symmetrical waveform like this. I'll show that in a moment why. So we can actually do a calculation, and let's pick an arbitrary value of, I don't know, let's say 4 volts and minus 4 volts. Whatever value you put in here, it's still going to work. If we take a measurement here, and this is our full cycle, so all we need is 2 measurements actually to work out the RMS value of a square wave. Here we've got 4 volts, and here we've got minus 4 volts, and we square them. We've got 2 measurements, so we divide it by 2 and take a root out of that. What that would be, that's 16 plus 16 divided by 2 root, so that's 32 divided by 2, so that's a root of 16. So that's 4, and that would be the RMS value of a symmetrical square wave. It's that simple really, and this is not an approximation in this case because this is a flat line, so this would be the actual accurate value of what this waveform is. As I said, this would work for any number. It will always work out and it will be accurate. Makes me wonder what would happen if we change the duty cycle of the waveform. Actually, in a case of a square wave, absolutely nothing. So let me explain why. Because we have those squares over here, which side of the zero the waveform is doesn't matter, because the square, you know, minus times minus plus and so on, this always flips it over to the positive side. This is always an absolute value of what this is. It doesn't matter which way the current is flowing. If it's flowing through a resistor, it will be heating it, and that makes sense. That's why there is that square over here. If you think about it, if this was the waveform, ignore this part for the purpose of this, but if this was a negative pulse like this, and we wanted to know the RMS value of it, of course it's symmetrical, so it goes to negative 4 or 5 volts or whatever that might be. It still doesn't matter, because it will get flipped over across the zero axis, and it will still be the actual peak value of the signal. For measuring a signal like this, again, we only need 2 measurements. Because it's a square wave, you take the positive peak value, negative peak value, square them, add them up together, divide by 2, and take a square root out of it. That is the true RMS value of a square wave signal. Let's have a look what would happen if we were dealing with a positive square wave. Positive square wave is a square wave that doesn't go to negative value. It simply stays at 0 for the low part of the cycle. This part here would be the full cycle of the square wave. The question is, can we apply the same principle to work out what that would be? If we take a measurement here and 5 volts, and that's 0 volts, so that would be 5 squared plus 0 squared divided by 2 and square root out of that. 25 over 2, that's 12.5, so that will be square root of 12.5. That's 3.5, this should be 3.5 volts. But that is wrong. We can't do that here, because this is not the pure form of this waveform. This is actually a complex waveform. Those are 2 waveforms superimposed on one another. Positive square wave can be considered as a symmetrical square wave of half the peak value. So in this case, voltage peak over 2, so if this was 5, this will be 2.5 volts and minus 2.5 volts, combined with a DC offset of 2.5 volts. 2.5 volts added to this square wave will produce that. When we combine those two, we know that this would be RMS value 2.5 volts, and this is 2.5 volts DC, so that's also 2.5 volts. Now, if we add those two together, we'll get 5 volts, which will not be the RMS value of this. It simply cannot be. with a positive square wave, what actually matters still, because again we are not going equally on both directions of the zero axis, is the duty cycle. In a case of a positive square wave like this, the actual RMS value of this should be, so the peak value, the high state if you wish, times the ratio of this time, so let's call that T high, divided by the entire period of the square wave, so divided by T. This is the duty cycle or aspect ratio. In this case it is 50%, Vp divided by 2, so that will be 2.5 volts. The duty cycle determines the RMS value of the signal, and that wasn't the case with a symmetrical waveform, because if we flip it over, then it kind of all evens out and it becomes a DC value. Positive square wave, where it goes to 0 and voltage and 0 and voltage, there's nothing to flip over, so the actual duty cycle makes a lot of difference. And if you think about it, the closer this duty cycle comes to be, almost a DC value, the RMS value would be tending towards Vp. So if this time was almost like 0.99% of the entire period, then the RMS value of this will be almost at 0.99% of the peak value of the signal, and that makes sense. And equally, if it went this way, so if it was just a tiny pulse like this, and then all at 0, and then another pulse and again at 0, this would have a very low value. So because the ratio of this time compared to the entire period would be very small, so that multiplier here would become very, very small, so the value would be tending to 0. And that makes sense. I hope that's simple to understand and we can get the interesting bits out of the way. We can have a look at what the multimeters will show and whether they actually are true RMS or maybe not. So let's make some measurements. To do that, I've prepared this little setup tablet with the interface for the ON 1022i oscilloscope, FY3200S signal generator, and that comes in here, and that is connected to 3 multimeters. As you can see over here, we have UT33D, this is the basic multimeter, non-true RMS. Then we have Aneng AN8002, supposedly true RMS, and Uni-T UT61E, again supposedly true RMS multimeter, that's what it claims. The ON scope is set up with DC coupling 1 volt per division. Signal generator, I've got it set at the moment to 50 Hz, 5 volt amplitude, so 2.5 volts peak. So let's switch the output on and see what we get on the screen and on the multimeters. A sine wave, 2.5 divisions up and down from the 0 axis. And please remember, this is at 50 Hz, so this is the frequency. Most of the multimeters, if they're not true RMS, they are calibrated to cope with exactly 50 or 60 Hz. First of all, UT33D is showing 1.4 volts, AN8002 shows 1.757 volts, and UT61E 1758. So those two show pretty much the same thing. True RMS voltage of a 5 volt amplitude sine wave. In addition to that, I've got oscilloscope doing some measurements here, and it's also calculating VRMS. It's reading peak-to-peak voltage of 4.96, just a hair under 5 volts, and RMS 1.729 volts, so 1.73. So a little bit lower than those two, definitely better than this one. Let's see if we change the amplitude up to 10 volts, 3.49 volts. Those two show thereabouts 3.5 volts. Traditional meter is reading quite low, but so far, to a degree, this is as expected. So we've got 3.5 volts, 3.5 volts, 3.2 volts. Well, it's a cheap meter. This is a 200 volts range. It's probably more suited to, voltages in the range of 100, 200 volts. But then on the other hand, would I plug it into mains? Yeah, it is what it is. And remember what I said about true RMS value does not depend on the frequency. So let's change the frequency a little bit. So I'm going to go to 150 Hertz. And again, averaging is producing funny elements, but that's not the waveform. It's only one stabilizes. It is what it is. I can actually switch off the averaging. 1 meter is complaining. So let's go to sampling. There we go. So now it won't do the artifacts. But yeah, we are now at 150 hertz. So yeah, 3.54, 3.53, 3.2. So again, 0.3 of a volt lower on this one, but yeah, the value is still the same. That's 250 hertz, 350, 450, 550 hertz. And as you can see, those two are holding up very well. This one starts to drop off even further, so it's 3.1 volts now. 650 hertz, the UT33D is reading 3 volts. True RMS meters are holding up a little bit higher. 950, still good. UT33D is half a volt out, so no good. That's 1.05 kilohertz, 1.15 kilohertz. No problem there whatsoever. I'll keep going. We are 1.75 kilohertz, and you can see the waveform is getting really messy. I'm going to auto calibrate that. That's at 10 volts peak to peak, and it's changed over to 2 volts per division and adjusted the time scale a little bit. So again, we can go a little bit higher. Okay, 1.95 kilohertz, and the Aneng starts to drop out. So 3.48. The UT61 is still at 3.53. If I go back, yeah, so 1.6 kilohertz, 1.65, 1.75, but 1.75 kilohertz it starts to drop off. It's dropped to 3.51, and if I keep going, it progressively goes down. That's 2.1 kilohertz, and yeah, that's 3.2 volts versus 3.53. So there's a significant difference in the measurement over here. What we're observing here is we've gone over the bandwidth of this multimeter. So the bandwidth for a sine wave for this multimeter is about give or take 1.6 kilohertz. Past that, it will show you rubbish. This one's still holding up, so just out of curiosity, I'm going to bump up the speed, 4.15 kilohertz, and still holding up. 3.5. Let's see when it drops below 3.5. We call that quits there. 13 kilohertz, and it's still holding up. As you can see, this one's showing absolutely nothing now. So according to this meter, there is no voltage. So let's keep going up and see what happens. That's 40 kilohertz, but it's starting to read a little bit high. Let's go stupidly high. 60 kilohertz, 22 kilohertz, jump to 3.6 volts. So let's call that quits on that one. So instead of actually dropping the voltage, the measurement, it bumped it up. So, but nonetheless, it's better frequency range on this one compared to the AN8002. But that's not the problem. You know, as long as you know the frequency range that your device should be operating in, it shouldn't be an issue. In the last video with this multimeter, what I've done is I've connected it to a device that was doing a square wave, and it was a positive square wave. So a little bit complex thing for this thing to measure. Let's go back down to 50 hertz. Auto range that on the oscilloscope. There we go. Yeah, so that's gone to 2 volts per division, 50 hertz, 3.52 RMS value. One might consider buying a true RMS multimeter to be able to measure signals other than the sine wave, triangle, trapezoidal, square, you name it. Will those multimeters be up to the task for measuring a square wave, for example? As I said, we are back to 50 hertz and 10 volts peak to peak sine wave. Let's change that to a square, and there we go. That is a square signal. We are showing 5 volts on both of those two meters. This one's showing a little bit high, about 5% high, 5.2 volts. It's still in the ballpark. Oscilloscope is showing 4.995, so 5 volts RMS value. And this is a 50% duty cycle, which doesn't actually matter, but it is a 50% duty cycle square wave. It's a symmetrical square wave, so it goes below 0 as far as it goes above 0 volts. Let's see what happens if we change the duty cycle of the square wave. So as I showed before, if we were to increase the duty cycle on this, it shouldn't make a difference whatsoever. It should stay at 5 volts, because whatever happens, if we basically take absolute values, this will be a DC. As far as measurement goes, this is a DC of basically this value here. 60%, 4.9, 4.8, 70%, 80%, 90%. Let's stop there. So at 90%, both of those are showing nonsense. The RMS value of this square wave is still 5 volts, and we're at 50 Hz, well within the bandwidth. This is not the measurements I would expect. Let's go back. So at 70%, we've got 4.5 volts on both of them. Both of those meters claim to be true RMS, but they cannot deal with a square wave of other than 50% duty cycle. If we go the other direction, so that's 20%, again, the RMS value of this will be 5 volts. Both of those meters show 4 volts right now, and this one shows 2. So this is completely out in the woods, but yeah, those are not showing the right value either. Here is another square wave. So this time I've changed the amplitude to 5 volts only. So 2 volts per division. We've got about 2.25 divisions up and down below the 0 line. 2.5 volts, no problem there. 2.3, 2.4 here, so this one's even quite close. Ballpark, we're all the same on all the meters. What I'm going to do now is apply offset. Now remember, we are DC coupled to the signal generator, so what I want to do is apply 2.5 volts offset. What that will give me is a positive square wave. Square wave with a 2.5 volts DC bias. Watch what happens. So first of all, the non-true RMS multimeter is completely out the window, showing 5.3 volts, which is, this clearly is not. It's a 50 Hz square wave, 5 volts amplitude. It's basically TTL logic level signal, 5 volts high, 0 volts low, and so on. Both of those meters show in a ballpark of 2.5 volts, and that is correct. So because this is a 50% duty cycle, time it takes from here to here divided by the length of the cycle of the period, 1/2. So RMS value will be 1/2 of the peak voltage, which is 5 volts. So 1/2 of that, 2.5 volts. Simple, and it works. And again, this is the waveform I was using. I think it could have been 12 volts at that time, I don't remember, but the same waveform in the essence when I was doing the video with this multimeter. What threw me off massively was what happens next and what I'm going to show you. So let's have a look at what happens if we change the duty cycle, which is what I was doing in that video. And we're at 50%. Let's go to 60%. So this should now be 6/10 of 5 volts, which should be 3 volts. Both of those show 2.43. So actually slightly lower than what they used to. This one's showing 6.4. I think this guy here is only for the company at this point, suffering badly. Let's keep going. 70, 80%. 80% of a 5 volts amplitude square wave, positive square wave, that should be 4 volts. But we've got 1.98 on both of those, and to me that's not the true RMS value. Maybe I am doing something wrong. Yeah, let me know in the comments, but from what I understand about true RMS and what it should be, this is not right. This should be 4 volts, not 2. 90%, that should be 4.5 volts, but we get 1.5 on both of them. Let's go back the other way, inverse the square wave. So there we go, 10%. This should be 1/10 of the 5 volts, so half a volt. We've got 1.5 over here, 1-ish here. So this one's actually a lot closer than the other ones. 20%, so this should be a volt, but we've got 2 volts actually on all of them. So that's not too bad, unless they're consistently wrong. 40% should be, what, 2 volts? 2.4 on both and 4.3 here. So yeah, I'm not sure what to make of this. Interesting thing to note over here is that the offset, the DC offset implied onto the square wave, does not make effect on those two multimeters at all. So this is with the offset. I'm going to go back down to 0 to make it back to symmetrical square wave, and as you can see, this measurement did not change whatsoever. This one did, somewhat correct-ish now, 0.1 of a volt out, 0.2, but yeah, in the ballpark. Applying DC offset throws this meter completely out of the water. It's completely wrong, 4.7 volts, almost double. RMS meters, they're completely unaffected by that. So the question is, can we measure the RMS value of a positive square wave with a true RMS multimeter? From what I see, we can't. If you think about it, adding a DC offset to a square wave like this makes no difference whatsoever on its RMS value as long as the DC offset is within the value of the amplitude of the signal. So let's see what happens with the multimeters. I've added 2 volts positive offset to this, and I'm going to make it one more beep and it will go to 3. So we go beyond the peak value of the square signal over here, which will mean that this square wave will never go to 0. It will never go negative and it will never go to 0. It will always be somewhat positive. So again, that's another example of why would you want to have a true RMS multimeter if you had a signal that sits on the positive side, and what will it measure? So let's go, 3 volts, still showing 2.5 volts. And now that is not the case, because right now the value of this RMS signal is 2.5 volts plus the half a volt that's above the zero. So that should be 3 volts right now, because we applied 3 volts DC offset, which was half a volt higher than the peak voltage of the signal, which in turn means that we've got extra half a volt implied onto this half a volt DC. So 2.5 plus half would make it 3. I hope that makes sense. So if we go higher, 4 volts, this should be 4 volts RMS value, but it's not. True RMS measurements are not valid in this case. It doesn't show the correct value. It should be 4 volts, but those are showing still 2.5 volts. And just if you were wondering, exactly the same thing happens if we go below the zero. So if we got negative offset, and again still see 2.5 volts on both of the true RMS multimeters. The other one shows 0, doesn't know what to do with it. This right now we've got 4 volts offset, that's 1.5 plus 2.5, so 4 volts. This should be at 4 volts true RMS value, but it's not. What do we get out of a true RMS multimeter? Well, definitely a bigger frequency response, it seems, bigger frequency bandwidth range for the voltages that we can measure. But in terms of measuring anything other than a sine wave, it gets a little bit tricky. I mean, you can measure probably other signals, not all of them. You have to be aware of what you're measuring. If it's a symmetrical square wave, it's fine. But if your duty cycle goes a little bit off either direction, or if you have any shift towards positive or negative side, any DC offset in the waveform, the measurements made by the true RMS multimeter are not valid. Disappointing, really. Perhaps I don't understand something, so by all means I'll keep my hands up. If someone can tell me that I'm wrong in my assumptions here, then yes, I'm wrong. But that's a bit of a marketing thing, you know. What would you expect when you get a true RMS multimeter? You expect to put it across 2 points and to be able to know, if you put a resistive load in that point, how much heating is going to happen. What's the equivalent DC voltage or current that would cause the same heating effect in the resistive load? That's what true RMS is. In case of what we observed here, it's clearly not the case to what's displayed on the screen. Here is another example of a triangle wave, 50 Hz, 5 volts peak to peak, 5 volts amplitude, and the RMS value is 1.43 volts, which is, this one is wrong as usual. Oscilloscope also shows 1.43. Applying any sort of offset to it, either positive or negative, not doing any good, making no change over here. Interestingly, on the oscilloscope, actually does make a difference. So if I go 1 volt extra, it will show me 1.83 RMS value, closer than those two, because applying a volt up or down over here would change slightly the RMS value of in a square wave, because the edges are so sharp, so quickly changes from one state to another. It doesn't matter how much offset you apply, as long as you stay with plus peak and minus peak voltages on opposite sides of the zero value, then makes no difference whatsoever. But in this case it does. But as we can see, the meters are not showing that, and this is not good, I think. Let me know what you think, what to make of this. This is true RMS disappointment of my true RMS expectations. It's not showing what I wanted it to show. Perhaps the true RMS multimeters are designed only to measure a sine wave, different amplitudes and frequencies, and the reading is a little bit more accurate. As you can see, this one's showing 1.4. Again, that's 50 Hz, so that's perfectly within the bandwidth of what this should measure. Even if this was using some lookup tables, it should be able to show a little bit more accurate. 1.75 is right what it would be for this waveform. I think my battery just died, which brings us to the end of this video, I guess. Please do let me know in the comments what you think of this. What would you expect of a true RMS multimeter if you haven't got one? And if you have one, yeah, let me know if there are any different true RMS multimeters that show what I would expect, or maybe my expectations are too high and something like I was talking about doesn't exist. For this video, that's it. Thank you for joining me. I hope you found it interesting. I found it quite amusing and annoying at the same time that I wasn't getting the right measurements, but hey, it's all for fun. So thank you very much for watching. Give me a thumbs up if you liked the video, and subscribe for more random electronics related stuff. For today, that's it. Take care.